Okay, welcome back. Dr. P here, and we're going to take a look at some characteristics of the SN2 reaction in this lecture video. So, the first thing is that we need to have a good nucleophile. Now, what is a good nucleophile? Well, let me give you some examples. Strong nucleophiles. These could be things like I minus, Br minus, Cl minus. We could have things like the Grignard reagent, RMGBr, RLi, acetylide ions, RC triple bond C, negative charge. Could have things like hydroxide, OH minus. We could have alkoxides, so a derivative of an alcohol. So hydroxide came from water. These guys come from alcohols. We could have the sulfur equivalent, HS, or RS minus. Actually, even RSH is a good nucleophile. Some other ones, we could have cyanide. That's a good nucleophile. That's probably about it for now. We'll see, we can get some other nucleophiles, but we'll run across those later on. Some weak nucleophiles include things like F minus, water, H2O, ROH. Ooh, I should add here NH2 minus and RNH minus, and actually something like amines are good nucleophiles, so ammonia is a decent nucleophile, and then RNH. Those guys are pretty good nucleophiles as well. Something like acetate will also be a weak nucleophile. Now, what are some features here of these good nucleophiles? Well, if we look at these, we can see, like, let's look at the halogens first. We see that we have chlorine, bromine, and iodine, or chloride, bromide, and iodide. And these are lower in the periodic table than fluoride. So one of our criteria is polarizability. Or the squishiness of the electron cloud. And as you go down in the periodic table, you get more polarizable because you've got greater area and the electron cloud can squish around a bit more. And when it squishes, it can sort of concentrate and flow into one side. So we see that here in the fact that Cl minus, Br minus, and I minus are all strong nucleophiles, while F minus, which is at the top of that group in the periodic table, is a weak nucleophile. Similarly, we see things like ROH is a weak nucleophile, but then one line below it in the group we have sulfur, and the sulfur equivalent of ROH is RSH, and that's a strong nucleophile. So as we're going down in the periodic table, we get larger atoms that are more polarizable. We can also have a negative charge. So all else being equal, the species with the negative charge would be a stronger nucleophile. An example would be water, weak nucleophile, versus hydroxide, a strong nucleophile. Similarly, alcohols versus alkoxy. Even within the strong nucleophiles, there are different nucleophile strengths. Rs- is a stronger nucleophile than RSH. RNH- is a stronger nucleophile than RNH2. Again, because of that negative charge, we've got more electron density. Now, some of these species, may be good bases as well. And we can see that in some of these examples. OH- is a good base, RO- is a good base, Grignard, alkyl lithium, acetylides, those are good bases. These guys are all good bases. RS- not so good a base. RSH, definitely not a good base. CN- not a great base. These guys not good bases. So some good nucleophiles are good bases. Others are just good nucleophiles. And when I say base, I mean Bronsted base. So Bronsted-Lowry base. Okay, so again, basicity and nucleophilicity are two different things. Okay, the nucleophilic strength is the tendency for the nucleophile to react with an electrophile, like say an electron-deficient carbon. Base refers to the ability of a molecule to remove a proton from something. So even though the proton is electrophilic, and a base would be functioning as a nucleophile in that case, we're focused more on how it works as a base. So again, some of these are good bases, others are not. None of these guys are strong bases. It's hard to have a strong base that is a weak nucleophile, but it can be done. Okay, let's see here. I think I'll maybe do a few of the characteristics in one video here. So what else do we need? We need a leaving group. Okay, and what is a good leaving group? What is a good leaving group? A good leaving group is stable after leaving. That is, it's not a strong base. So some examples would be, let's do R, let's do Rx, where X equals Cl, Br, or iodine. Okay, so for this guy, our leaving group is X minus. So if we have Cl minus, that's nice and happy. It floats around in solution. We could have something like, and this is what happened in the t-pentyl chloride synthesis lab. We could have H2O as a leaving group. Okay, so we have a protonated charged species, and when it leaves, it's neutral water. An example of a poor leaving group would be ROH. And then if we got stuff leaving, we'd get OH-. minus. And I could go ahead and draw in an arrow showing the flow of electrons here. I'll go ahead and do that. But this is a poor leaving group, okay, because hydroxide is a strong base. There's another really good leaving group, which is tosylate. And what tosylate looks like is the following. So there is our tosylate here. And this is a great leaving group. It's resonance stabilized. And that's one way to turn an alcohol into a good leaving group. So can turn an alcohol into a good leaving group by protonation or tosylation. Okay, so let's take a look at those. So with protonation, I'd have ROH, and I would treat it with H+, and I'll get ROH, positive charge there. So now I've got my good leaving group. With tosylation, I've got ROH, and I'll treat this with TSCl, tosyl chloride, which looks like tosylate, but it has a chlorine instead of this oxygen. And what happens is the oxygen here attacks the sulfur and kicks off the chlorine in a type of substitution reaction, and we get ROTS. Now, why would we want to do that? Well, these may be useful synthetically. So we definitely need a good leaving group. Interestingly, where are my nucleophiles? Here are my nucleophiles. A lot of strong nucleophiles are also good leaving groups. Well, maybe not a lot, but some are. I minus, Br minus, Cl minus. Those are all good leaving groups as well. Something like RO minus, not a good leaving group, but you know, RSH, that's a good leaving group. NH3, that's a good leaving group. So some strong nucleophiles are actually good leaving groups as well. So I just thought I'd mention that. All right, another thing to think about is the solvent. Okay, so we've looked at nucleophile, leaving group, and then solvent. And a polar aprotic solvent is what we want. And that's going to stabilize the transition state. But it's not going to stabilize carbocations. It's not going to stabilize the nucleophile. Maybe we'll say it doesn't over-stabilize nucleophile. So some examples of these are acetone, DMSO, which is dimethyl sulfoxide, DMF, whoops. I think acetonitrile is another one that's mentioned in the text. Now, none of these have acidic protons. None of these are hydrogen bond donors. It's probably a better thing to say instead of saying that they have acidic protons. None of these are hydrogen bond donors. They could accept hydrogen bonds. So these partial negative charges can help stabilize that partial positive charge of the transition state, in the middle of the transition state. But we're not going to have protons that could hydrogen bond and potentially stabilize a nucleophile too much. Okay, so again, these are stabilizing the transition state. Then the last area is the substrate. So this is the alkyl halide. And a less hindered substrate is better. That is, it reacts faster. So at the end of on the end of the scale for faster reaction, we'd have a methyl, and that's faster than a primary, which is faster than, just call it R2CHBr, faster than a secondary. These could be different R groups, doesn't matter. R3CBr, which is faster than a tertiary. And really, what we have here is methyl and primary are favored, and oops, let's make this a dotted line here. And secondary can do SN2, but a bit slower. And the reason for that is that the additional substituents will block the backside of the carbon from nucleophilic attack. So we'll say additional substituents block electrophilic carbon from backside attack. So let's take a look at that. So I have my cyanide nucleophile from last time, and I have my methyl bromide. And we see this is nice and open, so easily accessible to the nucleophile, can kind of come in from, you know, maybe a little different angle. Here's T-butyl bromide, well, T-butyl chloride actually, the green is chlorine, sorry about that. Anyway, it's harder. These are, there's more bulk here. Remember, these aren't exactly to scale, so you know there's a certain radius for this, and these guys just, they get in the way, these methyl groups. And the more stuff I have, the more hindered my electrophilic carbon will be, and the harder it'll be to get a nucleophile in. Especially if we had a larger nucleophile, it would be really hard to get that reaction. So less hindered substrates are better. Methyl primary, sometimes secondary, but tertiary just won't do, usually won't do SN2. All right, let's see how we're doing on time here. I do want to mention, and I mentioned this before, the inversion that happens, and I'll just draw that example out, or draw an example out. So let's say we had the following, and I made the model last time to show you guys, and we'll go ahead and treat this with NaCN, and whenever we see something like a sodium or potassium, we just cover that up, we'll ignore it. Na plus just floats around, so we have Cn minus is our nucleophile, and let's do this in DMSO. So those are SN2 conditions. And so what we will get is inversion. So I'll have Cn from behind, and the H will now be in front. And again, if we were going to look at it, we'd have CBr. And let me just tilt this around here. Let me rotate that guy. Let's rotate that. Well, I'll just draw it like this. CH2, CH3, CH3. And we'll go ahead and get nucleophilic attack, leaving group leaves. And then what we have is N, triple bond C, single bond C, H. That guy has been flipped over, CH2, CH3. And then that guy, the CH3 there, is in the back. And if you were to, determine the configuration, you'd have, in this case, for example, this guy is R, and then this guy is S. So we get an inversion of stereochemistry. And again, the mechanism explains why. Sorry, I forgot my BR minus then. There. All right. Well, that about wraps it up for the SN2 reactions. So be sure to look at some practice problems and practice identifying SN2 reactions. The mechanisms are relatively easy to draw. And I'll spend a later lecture video talking about drawing mechanisms in their different variations. Okay, next time we'll start looking at SN1. So until then, stay safe out there. Bye now.